Hello, Mr. Pardon here once again, and you just finished the preview activity for 1.6, and you got a little bit of a taste of what it means to be a second derivative, or what a second derivative is. Now, we're going to learn eventually exactly what is involved with a second derivative, but before we do, there's a couple things we have to take care of regarding functions. This definition I'm about to show you is quite wordy. And I'm not even going to read it to you. That's how wordy it is, because I don't think it's going to make sense. But you can see the bolded points of the definition. A function is increasing on an interval a to b, or a function is decreasing on an interval from a to b. Basically, you've had enough experience reading graphs that you know when we read graphs, we read them from left to right. If we're going from left to right on the graph, and the graph is going downhill, that is a decreasing interval, or a decreasing function. If the graph is going uphill, then we say the graph is increasing. You can read the definition if you want. If you're into that and you want to make some sense out of it, you certainly can. But I think just based on the picture, I think you are wise enough to figure out when a function is increasing or decreasing. Okay, now, this next part, even though it's wordy, is quite important. So if f is a function that is differentiable on an interval from a to b, meaning that the derivative exists everywhere within this interval, we say that f is increasing if and only if f prime of x is positive. All right. Similarly, we say f is decreasing if and only if f prime of x is negative. Now, the if and only if part means that the theorem goes both ways. So we can say that if a derivative is negative, the function is decreasing. Or we can say if the function is decreasing, then the derivative is negative. That's what if and only if means. Bottom line is this. As we look at this picture right here, we can see that from 0 to 2, the function is decreasing. So if you were to think of a slope of a tangent line anywhere from 0 to 2 on that interval, that slope is going to be negative. So we can say if the function is decreasing, then the derivative will be negative. Another way to say it, if we have a negative derivative, if we have a derivative that's less than 0, then we know that the function is decreasing. We can see that the function is increasing from 2, let's just say from 2 to infinity. So as soon as we make the slope of a tangent line, anywhere that the function is increasing, that slope of the tangent line is going to be positive. Said a different way, if a function is increasing, the derivative is positive, or we can say once we have a positive derivative, if we know f prime of x is positive, then we know the function is increasing. Now it comes to the second derivative. So let's take a few seconds just to analyze what the second derivative means. We know the limit definition for a first derivative, but consider a derivative of the derivative. That's a second derivative. And we denote this by f double prime of x. That's how we say this, f double prime of x. You'll never see it written the way that we have it here in the notes. So if we want a formal definition of this, f double prime of x is just the limit definition of the derivative of f. So it's the limit as h approaches 0 of f prime of x plus h minus f prime of x over h. Okay, now one of the things that you might have touched on in pre-calculus is concavity. How to tell if a graph is concave up or concave down. In an increasing function, there are three situations that happen. We have a function such as this. Most would call this like an exponential function. And we can say that the function is increasing for sure. As I read the graph from left to right, it's increasing, but it's increasing more rapidly as we go. The amount of increase increases. So think of the slope of a tangent line here, and think of a slope of a tangent line up here. We know that up here the slope of that tangent line is going to be greater. We can have a linear function that's increasing, but this is increasing at the same rate. Or we can have an increasing function such as this. It certainly is increasing, but it's increasing in such a way that the amount of increase is slowing down. All right, again, if you think the slope of a tangent line here at about this value, and think of the slope of the tangent line there at this value, we can see that the slope down here is going to be larger than the slope up here. So, in this first graph, the way we say this, it's increasing at an increasing rate. This graph over here, let me move my picture out of the way, is increasing at a decreasing rate. Hopefully that makes sense. Okay, now let's talk about decreasing functions, because this we have to get a little bit more careful with how we word things. This function right here is certainly decreasing from left to right. We can see that. But are you ready for this? It's decreasing at an increasing rate. Now, how can we say that it's decreasing at an increasing rate? Well, we have to consider the slope of a tangent line. We know the slope of the tangent line is going to be negative because it's a decreasing function. But the slope of the tangent line up here is going to be more negative than the slope of the tangent line here. So if we think about what's happening with those slopes, the slopes are actually increasing. It's going from, like, maybe let's say a -10 to a -5 to a -1. So the slopes are increasing. Think about it on a number line. This function right here would be decreasing, but this is decreasing at a decreasing rate. Again, slope of a tangent line right here might be like -1, but the slope of a tangent line down here is going to be like -10. I'm making these numbers up, but you get the idea. So because it goes from -1 to -10, it's decreasing at a decreasing rate. Okay, so basically with concavity, if we take a generic function like y equals x squared, we take y equals e to the x, which is an exponential function, these graphs would be considered concave up. All right, it looks like a cup. All right, it's like filling a cup. If you were to drop some water in there, it would fill the cup. Y equals -x squared, or y equals e to the -x, would be considered concave down. If you were to pour water over this graph, it would just drift down the sides. It wouldn't fill anything up. So these two graphs are referred to as concave down. All right. So what we can say is that when a graph is concave up, here's a graph that's concave up, think about what is happening to the slopes of the tangent line. Are the slopes of the tangent line increasing, or are they decreasing on a concave up graph? And we can say that the slopes of the tangent line are increasing. This slope right here is definitely negative. Maybe it's -5. This is -1. Then we go to +1, and then we go to +5. So if you think about those series of numbers, -5, -1, +1, +5, those are increasing. All right, so when a graph is concave up, we can say that f prime of x is increasing. On the other hand, when a graph is concave down, think about what's happening with the slopes of the tangent lines. Are they increasing or decreasing? They would be decreasing. Here we have, let's say, a +10, maybe a +1, then it goes -1, -10. So if you think about those series of numbers from +10, +1, -1, -10, those numbers are decreasing. All right, so here is another definition about concavity. This one I will read to you. Let f be a differentiable function on the interval from a to b. If f is concave up on that interval, I should say f is concave up on that interval if and only if f prime is increasing on that interval. F is concave down on the interval if and only if f prime is decreasing. So this definition goes right back to this picture here. Okay, that's all I got for you today.